Hello everyone, and today I'm gonna explain the quick select algorithm. Our agenda, we're gonna be talking about the problem definition or the problem statement, then discuss the strategy used, explain the algorithm steps, watch a visualization of the algorithm, see a Python code implementation, and finally walk through the time complexity analysis. Our problem definition, we are given an unsorted array of integers and an integer k, which must be within the bounds of the array, and our goal to find the kth largest element in our array. So we arrange the elements in the array such that the kth element is in its sorted and suitable position, and then return its value as our final result. The strategy employed in the quick select algorithm is decrease and conquer by variable. Why by variable? Because the reduction pattern of the problem size is unknown or undefined. The search space is based on the relative position of the pivot element, and the dynamic change of the left and right variables denoting the search range in the array is the main indicator of the search each iteration. Note that the algorithm works in place, so it doesn't need any extra space to achieve its goal, finding the kth largest element. Moving forward to the algorithm steps, we first begin with the initialization of our variables. Assign the left and the right denoting the search range in the array, initially to 0 and the length of the array respectively. Then enter the main loop, where we repeatedly choose a pivot based on the Lomotus partitioning. Lomotus partitioning works as follows. It chooses the pivot as the first index of the given array, then gets hold of its index, we will denote it as p. Then we loop through all elements of the array and check if any element smaller than the pivot value. If found, increment this p pointer and swap the values. Otherwise, we ignore any element greater than the pivot. Finally, we swap the values of the first element of the array at the left index, in other words, with the current p pointer index, and return the p, which indicates the current chosen pivot. And by this way, the chosen pivot will have all elements in the array having smaller values before it, while all elements after it having a great value in the array. Returning to our main loop, we are going to check whether we found our kth desired element or not based on the p returned and chosen from the Lomotus partitioning. If so, we reach our final result. Otherwise, we update the left and right variables. If the k is greater than the p, so we will look on the right subarray and only update our left pointer. If the k is smaller than the p, so we will look at the left subarray and only update our right pointer. Then perform another iteration in the main loop. Here's a visualization of how the algorithm works to help understand the methodology. Our k is 3, so we need to find the third largest element in the array. The p pointer will initially begin at 0 index, and the pivot value will be 7. We begin looping start from the 10. It is greater than the pivot, so we ignore it. 4 is smaller than the pivot, so we increment the p pointer and swap the values. 3 is smaller than the pivot, so we again increment the p pointer and swap the values. 20 is greater than the pivot, so we ignore it. And also 15 is greater than the pivot, so we ignore it. Finally, after looping through all elements of the array, we swap the pivot element 7 with the value at the p index, which is 3. Now, the p is equal to 2, which is less than 3, our kth desired element, so we perform another iteration in the main loop, calling the Lomotus partitioning function on the right subarray, starting from the 10, and we will take it as the new pivot. 20 is greater than the pivot, so we ignore it. 15 is also greater than the pivot, so we ignore it. Finally, we swap the pivot element, which is 10, with the value at the p index, which is also 10, because the p pointer hasn't ever moved. So we're basically swapping the 10 with itself. And then we're going to return the 3, which represents the new chosen pivot. So, congratulations, we found our kth largest desired element, so we return its value as our final result. It's 10. Moving forward, this is a Python code implementation for the algorithm. The quick select kth largest function, which takes two parameters, our array of integers and the kth desired element, and also the Lomotus partitioning function, which takes an array and the two variables, left and right, which specify the current search range in the array. Time complexity analysis. As for the average case, quick select achieves a linear time complexity of big O of n, and this occurs when the partitioning divides our array each iteration into two equal subarrays. So T of n equal T of n over 2 plus n. The n over 2 represents the half subarray, because basically we are dividing the array every time the half. And the n represents the complexity of the Lomotus partitioning function. If we continue on this pattern, and we have the size of the array each time, we can generalize that it computes to a linear time of big O of n. Speaking about the worst case, it occurs when the partitioning consistently reduces the search space by only one element, picking a pivot consistently as the smallest or the largest element, resulting in a quadratic time complexity of O of n squared. T of n equals theta of n plus theta n minus 1 plus 1. The 1 represents the basic operation of the comparison. and the n is the time complexity of the modes partitioning function. N minus 1 represents each iteration. If we continue on this pattern, we obtain theta of n multiplied to n plus 1 over 2, and we can generalize that it computes to a quadratic time complexity of big O n squared. If you want to see a practical example for the algorithm, here's our array, here's our k element. We are going to find the second largest element in this array, which is basically the 4. Its sorted position is here. So actually it outputs that the second largest element in the array is the 4. Thank you everyone for your time. Hope you enjoyed my presentation.